use the L'Hopital's rule to prove that this limit is infinity for any positive integer n. We see that the statement we're trying to prove is about all the positive integer n. So we're going to use induction to do so. To begin with, we need to define a property P of n to be this equality limit equals infinity. And then we know the proof with induction consists of 3 steps. First step is to prove that the base k is true, and then we're going to use the inductive hypothesis P of k to show that P of k plus 1 is true. At last, we can conclude that P of n is true for any positive integer n. So let's write that out. First step, we have P of 1. We need to show P of 1 is true. We see that P of 1 is true by doing some calculation. We calculate the limit when n equals 1. That is e to the x divided by x to the 1. Okay. We plug infinity into x, see that both the top and the bottom go to infinity, so it is clearly an indeterminate form that we can use the L'Hopital's rule. So we will take the derivative for the top as well as the bottom. So the top stays the same as e raised to power x, but the bottom becomes 1. And then this limit is clearly infinity, which tells us that P of 1 is true. Next step, we're going to show that P of k implies P of k plus 1 for any integer k greater than or equal to 1. What does that mean? Let's write out a sentence. We need to suppose that this is true, which means that limit is infinity when n equals k. So we suppose ex divided by xk is infinity. And then we want to show that P of k plus 1 is true, which is the limit is still infinity when n equals k plus 1. So we want to show this one. Ex divided by x, k plus 1, still infinity. So that is our goal, and this is what we have. Let's think about how we can achieve that goal by using this condition that we have. We do that by calculation. So we calculate this limit x k plus 1, right? We see when we plug infinity into x, we have the top and the bottom, both of which are infinity. So we can take one step of the L'Hopital's rule to derive the top and the bottom. So ex divided by k plus 1 bracket times x to the k. And then we can see that this 1 over k plus 1 is a constant that we can pull out. So we can write it as 1 over k plus 1 multiplied with this limit x goes to infinity ex divided by xk. But in the inductive hypothesis, we have already known that this limit is infinity. Okay, so by using this inductive hypothesis, we can just simply replace this expression with infinity, and then we're going to come to k plus 1 multiplied with infinity. And because k is already assumed to be an integer greater than 0, so this k plus 1 will not affect the sign of this infinity, which tells us that final answer is infinity. Now we see that we have successfully proved that limit of this is infinity, which is what we need. That is exactly the statement P of k plus 1. Okay, so the second step is already finished. The last step, we can just conclude. That P of n is true for any positive integer n, which is n plus. Okay, so by doing this question, we can see that the exponential function grows way faster than this power function for any positive integer n as s approaches infinity. And that's the reason why it always goes to infinity.